Morning. I'm Rajasekaran, working as Associate Professor in the Department of Electrical and Electronics Engineering of PSN College of Technology. So today we are going to see about the subject Electromagnetic Field Theory. It's a course for third semester triple students, Electromagnetic Field Theory. It's a theory about the electromagnetic fields. So we have electric fields as well as magnetic fields. Combinedly, we can call it as electromagnetic fields because they are interdependent. Being interdependent, the two fields are combinedly together known as electromagnetic fields. Theory about electromagnetic fields. Here we have the syllabus. So being a vector, electromagnetic field is a vector quantity. We have some basic fundamentals on the vectors, scalars and vectors, the various operations on the vectors, and also the coordinate system. Coordinate systems, rectangular, cylindrical, and spherical coordinate system, using which we can analyze the electromagnetic fields. For that purpose, also we have the three systems: coordinate system, cylindrical, rectangular, and spherical coordinate systems. The second unit deals about electrostatics. So it is purely on electric fields. Electrostatics is a study of electric fields. Electric field is nothing but the field produced by static charge. Whenever we have the charge at rest, the field around the resting charge is electric field. Study of electric field is electrostatics, in which we have the Coulomb's law, the basic fundamentals law on charges, Coulomb's law. Then finding electric field for different systems. For example, a line charge, a circular charge, or a disk of charges at rest, we can find the electric field strength. Electric field strength due to this line charge, circular charge, and a circular disk. Here we can find the electric field intensity, and also we have the potential due to the charge, and finding potential at any point due to line charge or circular charge. We can identify the potential also. So second unit deals about electrostatics. Third unit deals about magnetostatics. The magnetostatics is a study of magnetic fields. Study of magnetic fields is magnetostatics. So like electric fields, here also we have charges. The charge is the prime source for the magnetic fields, but here the charge is at motion. So magnetic field is a charge, is a field due to the moving charges. Moving charges creates the magnetic fields. Study of that magnetic field is magnetostatics. So study of charges or moving of charges is nothing but current. So current is the source. Here current is the source for magnetic field. So due to current we have magnetic field. So in this chapter, in this unit, we have to find the magnetic field intensity around a moving charge, or a conductor carrying the current. We can find the magnetic field intensity or the strength of the magnetic field. So by using the like Coulomb's law in electrostatics, here we have the Biot-Savart law. Using Biot-Savart law, we can find the magnetic field intensity due to a current carrying wire, a circular wire. We can find the magnetic field intensity. Also, we can find the Lorentz law of force. Lorentz law of force is nothing but it is the combination of electric force as well as magnetic force. So combinedly, the force due to a charge which is moving. So which is having the two forces, the force due to electric and and also the force due to magnetic fields. That is known as Lorentz law of force. And also finally we have magnetic vector potential. Like electric vector potential, here we have magnetic vector potential. It is potential due to the moving charge. So being a vector quantity, it is vector potential. Electric potential is a scalar potential, but magnetic potential is a vector quantity. So next in unit 4, we have electric and magnetic fields in materials. Previously we have studied the field, electric field and magnetic field due to the charge at rest and the charge in moving. But what will be the effect of these electric and magnetic fields on materials? Electric and magnetic fields in materials. The materials, electric material, capacitor is an electric material. Magnetic material is inductor. So respectively, inductor and capacitor are magnetic and electric materials. So what about the electric and magnetic fields in these inductors and capacitors? So that will be there in unit 4, electric and magnetic fields in materials. The last unit is about electrodynamic fields and electromagnetic waves. Electrodynamic fields and electromagnetic waves. So electromagnetic waves. The electromagnetic field is propagated in the form of waves. So every signal in the universe can be communicated, transmitted as an electromagnetic wave. So study of electromagnetic waves is very important. And characterizing these electromagnetic waves using some equations, derived differential integral equations, we can derive the properties of electromagnetic waves. For the analysis of electromagnetic waves, how the Maxwell's equation, how well it is importantly used in the analysis of magnetic waves. So that can be analyzed, and derivation of the Maxwell's equation for different type of conductor nature and medium nature, how to derive the electromagnetic waves. So that topics are going to detail in this unit 5. Okay. Okay. So as previously said, electrostatics is the branch of electromagnetics dealing with the effects of electric charges at rest. Electromagnetics is everywhere, because everywhere we have charges. In the universe, the infinitesimal particle is charge. The most infinitesimal particle is charge. So due to charge, we have electromagnetic field. That's why we can say as electromagnetic is everywhere. Examples of electromagnetic applications. So today, there is no application without the electromagnetic waves and their related products. These are all some examples for appliances using electromagnetic waves. It's a three-dimensional wave. Electromagnetic field is a three-dimensional wave. So electromagnetic, the charge is a fundamental. The charge value for electron is a negative charge. Its charge value is 1.602 into 10 power minus 90 coulomb. So very the most infinitesimal fundamental particle. And 6.24 into 10 power 18 electrons carry a charge of 1 coulomb. So 1 coulomb of charge is nothing but 6.24 into 10 power 18 electrons. So this much amount of electrons combined together constitute a charge of 1 coulomb. We have positive and negative charges. The charge is also being treated as a conserved one. Scalar and vector fields. Examples for scalar and vector fields. Scalar, voltage, current, energy and temperature. So quantified only with the magnitudes. These are all scalars: voltage, current, energy and temperature. Vector is a quantity which can be quantified with both the magnitude as well as the direction. So they are vector quantity. For example, velocity, momentum, acceleration, and the force. Electromagnetic field is also a vector quantity. So many examples for scalar fields. So vector fields is quantified both by the magnitude as well as the direction. Example is also the magnetic field is a vector field. Surrounding a magnet, we have magnetic fields. So being quantified both in magnitude as well as the direction. It is a vector field. Unit vector. So unit vector is nothing but it is a unit vector which is directed along any vector. Along any vector we have the unit vector. So how to quantify the unit vector? Suppose A is a vector. A is a vector. Its unit vector is the vector divided by the modulus of that vector, the same vector. So unit vector along a vector A is nothing but the vector itself, that is A, vector A divided by the magnitude, the modulus of the vector A. So that will give the unit vector. In the vector we have two products, the basic things, dot product and scalar product. The mathematical meaning of dot product and their properties. Cross products. So it is a vector. Dot product is a scalar quantity. Cross product is a vector quantity. And how to quantify the dot products? A cross B is nothing but given in a matrix form. It's a 3 by 3 matrix. In first row we have the unit vector along the three direction x, y, z, ax, ay, and ez. The second row we have the first vector, the coordinates of the first vector in x, y, z direction, that is ax, ay, and az. The third column is the coordinates of vector b in x, y, z direction, ax, by, and az. Cross product is a vector quantity. The properties of cross product is not commutative. A cross B is not equal to B cross A. It is anti-commutative. A cross B is equal to minus of B cross A. It is not associative also, but it is distributive. Scalar triple product. So scalar triple product is a scalar, but vector triple product is a vector. So vector representation in electromagnetic fields, we have three vector representation: rectangular coordinate system, cylindrical coordinate system, and spherical coordinate system. For example, sheet is a rectangular. Wires and cables, they are represented in cylindrical coordinate systems. Spheres, spherical system. So according to the shapes, we can use the three types of coordinate system: rectangular, cylindrical, and spherical. Coordinate system means capturing the information of a particular point in the space by different methods. That is called coordinate systems. The three types: rectangular, spherical, and cylindrical. Rectangular coordinates are x, y, z. X, y, z. The three coordinates which are perpendicular to each other: x, y, z. X, y, z are the length coordinates. X, y, z are length coordinates. Spherical, we have the coordinates of r, theta, and phi. Here, r is the only the length coordinates. The other two are, that is theta and phi. They are angular coordinates. So one length coordinate and two angular coordinates, theta and phi. It constitutes a sphere. In cylindrical, we have two length coordinates and one angular coordinates, z, r, and phi. So z is the length, r is also the length coordinate, phi is angular coordinate. So Cartesian is of x, y, z. Spherical is of r theta phi. Cylindrical is of r theta and z. In Cartesian, we have all the three coordinates as a length coordinates. In cylindrical, two length coordinate and one angular. Spherical, one length and two angular coordinates. So rectangular coordinate system. Here x is x, y and z all are varying from minus infinity to plus infinity. In cylindrical, r is varying from 0 to infinity, phi is varying from 0 to 360 to pi. Z is varying from minus infinity to plus infinity. In spherical, r is varying from 0 to infinity, phi is, as previously mentioned, it is from 0 to 360. The theta is varying from 0 to 180, 0 to pi. So we can have the relation between all the three coordinate system. What is the relation between cylindrical and Cartesian? Cylindrical and Cartesian. So rho is a cylindrical coordinates. How to get the cylindrical coordinate rho from the Cartesian? Rho is equal to root of x square plus y square. And phi is a cylindrical. Phi in terms of Cartesian, it is tan inverse of y by x. Then x is equal to rho cos phi and y is equal to rho sin phi. Similarly, relation between cylindrical and Cartesian unit vectors. In unit vectors also we have the relationships. These are the relation between the unit vectors of cylindrical and Cartesian. And relation between spherical and Cartesian. R, theta and phi. These are all the spherical coordinate system. R is equal to root of x square plus y square plus z square. It's a relation. How to get the spherical coordinate R from the Cartesian coordinates x, y and z. Theta is a spherical coordinate. How to get it from the Cartesian? Theta equal to tan inverse of root of x square plus y square by z. And phi is equal to the tan inverse of y by x. Then how to get x, y, z? The Cartesian coordinates from the spherical. X is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. Some problems using which we can convert one coordinate system to another coordinate system. Area integrals. Integration over two delta distances is area integrals. Examples. So having x and y, you can find the area integral. So area is equal to, it is integration over x as well as y. The third coordinate is a constant. So here r equal to constant and phi equal to constant and theta equal to constant in spherical coordinates. Surface integral is nothing but the area integral. So vector is normal to surface. It is dx into dy into the unit vector az, because the ds is in z direction. This is perpendicular to both x and y. That's why we have mentioned the unit vector in z direction. Line integrals. It is about only one coordinate. dl equal to dr and dr. Or dl equal to r d phi into a phi. So r d phi is a length coordinate. R d phi, r multiplied by d phi is a length. It is in the phi direction. So a phi. Examples for surface integrals. volume universe, here we have three coordinates, all the x, y and z. dv equal to dx, dy and dz. Then definition for gradient. So gradient is nothing but it is a differentiation of any vector. Differential of any vector is known as the gradient. It can be represented as del dot A. Del dot A. So gradient of a vector A is nothing but the dot product of the del operator and the corresponding vector, which gives the divergence of any vector. So divergence of any vector. For all the coordinate systems, we can get the gradient. Summary of the vector system. So gradient of any vector is a vector. Divergence of any vector is a scalar. Curl of a vector is a vector. Laplacian is a scalar. Gradient is a scalar field. A vector field. Divergence is a vector field. Curl is a vector field. Gradient is del phi. Divergence is del dot v. That means divergence of vector v. Curl of vector v is Laplace e. Laplacian is del square of phi. So divergence theorem. Later we have to study about divergence, Gauss divergence theorem. Stokes theorem. So they are relating the area integral and the volume integral. So using this Stokes and divergence theorem, you can relate the area integral, line integral and the volume integral. Curl. So curl can be defined as the cross product of the del operator and the corresponding vector. For every vector A, we can give the curl of the vector A is nothing but the cross product of del and the corresponding vector A. So as usual, the vector product it can be represented in the matrix form. Del cross A can be represented in the matrix form. So divergence and the curl. Stokes theorem. Del cross A ds. Surface of del cross A ds is equal to the line integral. The line integral is equal to the surface integral of curl of that vector. Surface integral of curl of that vector. So with that we can wind up the study of vector fields, which will be used in electromagnetic fields. Electrostatics is the study of electric fields. Here the fundamental law is Coulomb's law. Electric charge, positive and negative charge, the charge of an electron, charges we have point charge, line charge, surface charge and the volume charge. So line charge is nothing but the charge per unit length, quantified as charge per unit length, as line charge density. Surface charge density is the charge per unit area. Volume charge density can be represented as charge per unit volume. So using which the charge, the unit for line charge is Coulomb per meter, line charge density. The unit for surface charge density is Coulomb per meter square, and the unit for volume charge density is Coulomb per meter cube. Electrostatic force. So electrostatic force is nothing but the force between two charges. We have a force between two charges. So which may be repulsive or attractive. The force between any two charges is repulsive or attractive. So in which we have to consider the permittivity of free space, which can be given as 8.85 to 10 power minus 12 farad per meters. Relative permittivity epsilon r, and absolute permittivity epsilon is epsilon naught into epsilon r. Coulomb's law gives the force between two charges. So it says the force between any two charges, taking Q1 and Q2, two charges which are separated by a distance R12. The force between the two charges is equal to K into Q1 Q2 by R12 square. That means the force between any two charges Q1 Q2 is directly proportional to the product of the two charges Q1 and Q2, and it is inversely proportional to the distance between the two charges. The square of the distance between the two charges Q1 and Q2. So in this way we can write F12, the force between charges 1 and 2 is equal to K, a constant, Q1 Q2, the product of the two charge magnitudes Q1 and Q2 divided by R12 square. R12